Okay, so we looked at binomial probabilities and binomial settings. Couple other things that we need to talk about binomial random variables. The first is finding the mean or expected value. So this is n times p. So n is the number of trials we're doing, and p is the probability of success. So if you think about it like if you were going to flip a coin 10 times, how many times would you expect to get tails? Well, 10 times 0.5 would be 5. So we would expect 5 times we would get tails. Doesn't mean it would happen exactly every time, but that would be the average number. Okay, and then for standard deviation, we can also find the standard deviation of a random variable, and that formula is here. The square root of n times p times 1 minus p, right? So like if p was 0.25, this would be 0.75, and then we multiply that by n and take the square root. Make sure that you remember these things can only be used for binomial distribution. So if we're looking at something that is not binomial, then we can't use those formulas. All right, so as an example, we have students who are trying to guess whether the water they taste is bottled water or tap water. And so we want to calculate and interpret the mean. Okay, so mean is just n times p. So 21 students times the probability of 1/3. So that is 7. And then here's sort of the template that we're going to use for interpreting the means. Remember, we're always going to talk about many because probability is only predictable over the long run. So after many trials, the average number of correct guesses by Mr. Hogarth's class out of 21 is 7. Okay, same thing with standard deviation. We just plug into the formula, okay, and so the standard deviation is 2.16, and that interpretation is going to look very similar to our other standard deviation interpretations. So the number of correct guesses out of 21 typically varies by 2.16 from the mean of 7, all right, and so we want to make sure we're using that word typically varies, because everyone is not going to be the same, but that is the like average amount that they vary by. Okay. Something that's important to note with binomial distributions, when we're flipping a coin or spinning a spinner or things like that, like each of those trials are clearly independent. But sometimes we have to select students or people from a group. And anytime we are selecting people, we're typically doing it without replacement. Like if I'm choosing students from a class and to survey, if I pick one, I'm not going to put that person back in the group to be chosen again. All right, so that would, then those things would be not independent, which would mean we could not use the binomial probability rules. But someone with a lot of time on their hands did some calculations and found out that if we have a big enough population, the probabilities are approximately binomial, so it's close enough that we can still use the rules, all right? And so the rule is as long as your sample size is less than 10% of the population, all right? And so this is called the 10% condition. So if I'm sampling without replacement, that is okay as long as my sample is less than 10% of the population. So we'll look at an example. We have a survey of 500 US teenagers, and we want to know if they have a debit card, and X is the number of teens in a random sample of 500 who have a debit card. All right. 500, if we're sampling 500 teenagers, it's pretty safe to say that that's less than 10% of all of the teenagers in the United States. So we can use a binomial distribution here. And then if we want that probability, that 50 or fewer, this again, I would use your calculator because otherwise we would be doing the probability of 0 plus 1 plus 2 plus 3 plus 4, and we'd be doing a whole lot of math. Okay, and so that would be 0.0932. All right, the other kind of random variable that we're going to look at besides binomial is a geometric random variable. Okay, so for geometric settings, still 4 conditions, just slightly different from the binomial ones, okay? Still got to be binary. So each outcome is either a success or failure. Still have to be independent trials. All right. Still, number 4, have to have the same probability. The difference between the binomial and the geometric is the number of trials. So in a geometric setting, we are counting how many trials it takes to get success, versus in a binomial setting, we have a fixed number of trials ahead of time. All right, so if we take flipping a coin as an example, if I say I'm going to flip a coin 10 times and record the number of times that it lands on tails, that's a binomial setting. If I say I'm going to flip a coin until it lands on tails and count how many times it takes me, that would be a geometric setting. Okay, so we talked about using bins to help us remember what we have to check for a binomial setting, and then for a geometric setting, it would be bits. Okay, so bins and bits are those acronyms to help you remember when you are verifying which formula to use. So here is our formula for geometric probabilities. All right, so the probability that it takes whatever number of successes is equal to 1 minus p, so p is the probability of success, raised to the k minus 1 power, and k is the number of successes. All right, and then that is multiplied by p. So let's look at an example. I'm going to let you pause and read through this. Okay, so the probability that they get exactly 10 homework problems. So we want the probability that y is equal to 10. The probability of success is 1 over 7 or 0.143 because they're 7 days and they're picking from. Okay, so that's going to be equal to 1 minus 0.143 to the k minus 1. K is 10, so to the 9th power. All right, and then times 0.143. We can also do these in the calculator, all right? And same as the binomial, if we want the probability that x is equal to a number, so it takes exactly 10 tries, we are using GPD, or if you have a TI, it's Geomet PDF. Both of those things are in the same distribution menu as before. You're just looking for the geometric ones. And then just like before, we are putting in p. You can put it in as a fraction. That is totally fine. Or if they give it to you as a decimal, put it as a decimal. And then the x that we are looking for is whatever x is equal to. So in this case, it would be 10. All right, so we go back to our example. Same lucky day game. This time, we want to find the probability that they get less than 10 homework problems. Okay, so the probability that they get less than 10, one way that we could do this is a lot of writing, but we could find the probability that they get 1 or 2 or 3 or 4 or 5, 6, 7, 8, 9. All of those numbers are less than 10. That's a lot of work though, especially when we have calculators. So anytime we want less than, we are using GCD or geometric CDF. Just like the binomial problems, the calculator is finding the probability that x is less than or equal to whatever number you want, whatever number you put in. So the problem asks for less than 10. In the calculator, we're going to type that as less than or equal to 9 because the calculator is always less than or equal to. All right, and then we're also going to look at expected value or average for geometric random variables. All right, so this would be a graph of what that game would look like. So the probability of getting 1 homework problem, 2, 3, 4, and so on and so forth. Okay. If we wanted the mean or expected value, how many questions do we expect that the class will get? That formula for geometric random variables is 1 over p, where p is the probability of success. Okay, so we want the expected value for the lucky day game. All right, 1 over p is 6.993, or basically 7. So the expected number of problems that we would think the class would have on average would be about 7. All right, and again, that's the interpretation as well, just like the interpretation of the binomial expected values. After many, many trials, The average number of picks it takes to match the lucky day is 7. And that's all we got for this last part of 6.3.